related to the life cycle assessment of e-diesel production. The transport sector in 2022 accounted for the 21% of the global carbon dioxide emissions. And among these 21%, the 38% was related exclusively to cars and vans. And it is in this context that the European Commission proposed with the Fit for 55 legislative package to ban the registration of new internal combustion engine vehicles beyond 2035. However, they also made a proposal of continue to allow the sale of this type of vehicles, which are the conventional cars and vans, if powered exclusively by e-fuels. But what are these e-fuels? Electrofuels, also known as e-fuels, are synthetic fuels produced combining hydrogen and carbon monoxide using renewable electricity. Hydrogen is typically produced through water electrolysis, while carbon dioxide can be captured from different sources like air through direct air capture, industrial flue gas, or gases derived from biomass conversion. According to the targeted e-fuels, different conversion pathways are available, but we focus specifically on one, which is the Fischer-Tropsch synthesis. The Fischer-Tropsch synthesis allows to convert a synthesis gas, also known as syngas, which is a mixture of hydrogen and carbon monoxide, into a wide range of hydrocarbons, which are collectively known as syncrude. This syncrude presents physicochemical properties similar to those of the conventional crude oil, and it contains different fuel fractions, such as gases, petrol, kerosene, diesel, and oxys. The interest in e-fuels arises from its three main attributes, which are: the first one, their physicochemical properties, so they can be used directly in the existing fuel distribution systems and also in the vehicle fleets without major modifications. They also have carbon management potential, in particular when carbon dioxide is sourced either from air or from gases derived from biomass conversion. A closed carbon loop is established, as once the e-fuel is combusted, it releases carbon dioxide in amounts that are equal to the previously carbon dioxide captured, while when e-fuels are produced using carbon dioxide derived from industrial flue gases, the environmental benefit lies in the use of carbon dioxide emissions to produce a fuel intermediate rather than releasing these emissions directly into the air. And in the end, using renewable electricity and converting it into chemical energy, they allow for energy storage, long-distance transport, and they can also contribute to enhance the grid stability. On the other side, however, their production pathway is highly energy intensive. They currently come with high production costs, and up to date, a very limited number of production facilities exist. So the goal of our assessment was to evaluate through the life cycle assessment methodology the environmental impacts related to e-diesel production, subsequently compare the evaluated impacts with those of conventional fossil diesel in order to assess whether and under which conditions e-diesel might present environmental benefits over fossil diesel. However, there was a huge problem. We couldn't have access to non-confidential primary data from an operational production plan, and so we decided to use technologies that are operating at industrial scale for which public data are publicly available. These are the main technological assumptions we've made. We have considered two different electricity mixes, the 2023 Italian grid mix and its corresponding renewable-only subset. And we also considered two different carbon dioxide sources. So air through direct air capture technology and carbon dioxide captured from the flue gas of a cement plant. We have performed a cradle-to-gate analysis, meaning that all the processes going from the raw material extraction to the actual fuel production were considered within the system boundaries. The functional unit chosen was 1 megajoule of produced diesel, and I would like to focus more on the multifunctionality problems we had to face. In LCA, multifunctionality arises when a system produces more than one product. So there is a challenge in deciding how to allocate the impact of a system among the different products. In this case, we had two multifunctionality cases. One related to the Fischer-Tropsch fuel, as it contains diesel, waxes, and naphtha. And in this case, we performed an energy-based allocation. So 36.5% of the overall impacts were attributed exclusively to e-diesel. While concerning the carbon dioxide-related multifunctionality, it was a bit more tricky, because in the cement plant, we have the simultaneous production of both clinker and carbon dioxide. And according to how you see the carbon dioxide, you can use an approach or another. So specifically, if you consider carbon dioxide as a waste, the cutoff approach should be used. And according to this method, you have to identify the point at which the material under examination, so in this case, the flue gas containing carbon dioxide, shifts from having a negative to a positive market value in order to define how to divide the impacts among the waste generating system and the recycling system. In this case, we decided that the e-fuel producer need for the flue gas was enough to give to the flue gas a positive market value, and so we identified the point at the inlet of the capture unit. This means that all the impacts upstream the capture unit were given to the cement plant, while all the impacts downstream the inlet of the capture unit were given to the fuel producer. So within the system boundaries, we considered all the impacts related to the capture unit, and in this case, the carbon dioxide enters in the system boundaries burden-free, so without impact. Conversely, when carbon dioxide is seen as a co-product, the substitution via system expansion approach can be applied. In this case, using capturing carbon dioxide from a flue gas prevents the emission of these carbon dioxide in the air. So the environmental burdens related to the conventional system, which is the cement plant without the capture unit, are subtracted from the analyzed system, so the e-fuel production pathway. So in the end, like in the previous case, the impacts related to the capture unit are included within the system boundaries, but here the carbon dioxide is modeled as a negative flow, not burden-free, as a negative flow introducing a credit, which is representative of the temporary avoided emissions. Then there is also there can be another discussion on how you allocate this credit, but we decided to consider that the cement plant originally didn't have the carbon capture unit and that the e-fuel producer takes the full financial and operational responsibility of the capture unit. Here we have the main mass and energy flows, in yellow the mass flows and in blue the energy flows. related to the production of 1 kilogram of e-diesel. And I would like you to focus on the electrolysis phase and on its electricity consumption, that, as you can see, it has the largest share of electricity demand within the whole production pathway. Moving to the results, we have considered 16 impact categories, and in 6 different scenarios. So differing for the 2 electricity mixes considered, 2 carbon dioxide sources, and the 2 different approaches used to solve the carbon dioxide related multifunctionality. Here we have the impacts of the fossil diesel, and the results for the 6 scenarios are presented as percentage variation compared to the fossil diesel impacts. Where you see red values, it means that the impacts are higher than the fossil diesel one. When they are black, it means they are comparable because they fall within the range of plus and minus 10%. When they are green, instead, they present an environmental improvement over fossil diesel. And as you can see, the improvements are not that big and not that many, as we have improvements only when carbon dioxide is sourced from the flue gas of a cement plant, and in terms of climate change impact category, only when the substitution approach is used and the renewable electricity mix is used. Here we have a 70% reduction over fossil diesel, while the other category is the fossil resource use, where the choice of the approach doesn't affect the results. And in fact, as you can see, all the impacts in categories other than the climate change are the same between the cut-off approach or the substitution approach. These are the remaining 8 impact categories. As you can see, no improvements were observed, but only higher impacts. And then we have performed a contribution analysis. So this graph is a little tricky. We have 16 groups of bars. Each group of bars is related to an impact category. Every group is made of 7 bars. The first 6 are related to a specific scenario, while the last one, so the gray bar, is related to fossil diesel. For each scenario, we have divided the contribution of the 3 main stages in the production pathway, being hydrogen production, carbon dioxide capture, and synthesis. And as you can notice, in 14 of the 16 impact category, hydrogen production represents the main contributor in determining the overall impacts, except for 2 impact categories, which are the freshwater ecotoxicity and the ozone depletion, and only in scenarios where direct air capture is considered. In this case, carbon dioxide capture accounted for more than 50% of the overall impact, and this is mainly due to the sorbent production, the sorbent used for the capture of the carbon dioxide. While in all the remaining cases, hydrogen is the main hotspot, and this is due to its high electricity consumption. Indeed, electricity was identified as the main hotspot within the whole production pathway. We have decided also to perform a break-even analysis, specifically on the carbon intensity of the electricity mix. So you see an horizontal line which represents the climate change impacts of fossil diesel, which is not a function of the electricity mix you use, while for the remaining lines represents each carbon dioxide capture option. So the purple one uses the cutoff approach to solve multifunctionality. The yellow one refers to direct air capture, and the last one refers to the adoption of the substitution approach. Each dot corresponds to the resulting climate change impacts estimated using a specific grid mix from an European country. As you can see, currently, only 4 European countries would allow to observe climate benefits of a diesel production over fossil diesel. And these are Norway, Sweden, Iceland, and France. And specifically for the scenario considering direct air capture or applying the substitution approach. Well, for what concerns the cutoff approach, it will never bring a climate benefit if not for carbon intensity below minus 1.35 grams of carbon dioxide equivalent per kilowatt hour, which is basically impossible because it would require the electricity generation to absorb carbon dioxide from the atmosphere. So in conclusion, there is a very limited access to primary data, and a stronger industry collaboration should be encouraged in order to truly assess the environmental promise of e-fuels over fossil diesel. E-diesel production could present environmental benefits only in terms of climate change and fossil resource use, and only under specific circumstances. And the approach used to solve the carbon dioxide multifunctionality highly affects the determined climate change impacts, while all the other impacts remain unaffected. And so a harmonized LCA framework should be defined in order to guarantee the comparability of results in different analyses. Hydrogen production was identified as the dominant hotspot, responsible for more than 50% of the impact in 13 of the 16 impact categories, and electricity is definitely the hotspot in the production pathway of a fuel. So without not even renewable electricity, but with electricity presenting a carbon intensity approximately lower 100 grams of carbon dioxide equivalent per kilowatt hour, e-diesel would never achieve climate benefits over fossil diesel. And these are the references I will give if you're interested, and thank you for your attention.